test requirements. That's the example we have seen. Okay, for this graph, all the prime paths that you have would be what we have: 1, 2, 3, 4, 5, 6. Only has 6 prime paths instead of infinite number possible paths. Okay. And if you want to achieve like test path, want to achieve prime path coverage, you only need 2 test paths. Okay. I guess the next question is that how we're going to first compute prime path, right? If you want to achieve prime path coverage, you have to know what the prime path you have in the graph, and then how you can generate test path to cover every prime path. That's what we are going to discuss next. Okay. But this is how it looks like if you use prime path coverage. And as you can see, this is different. Well, this execute the twice, right? One without the loop, and the other executes the loop twice. And before we discuss how we're going to actually compute the prime path and how we generate test path to achieve prime path coverage, we want to discuss a couple of concepts as well. Okay, that has practical significance. Tool. Anyone remember the concept of a tool? If we say one path towards another path, what does it mean? The second path has to appear in the first path, right? Path A towards path B. It means in path A, you have to be able to find path B. That's the definition. Okay. So look at this example. Like we have one path, A, B, B. This is the path, right? A, B, D, 2 edges. And we have another, actually this is the test path. S0, A, B, C, E, S, F. Pass this path toward this one. No, right? Why no?
Order matters.
Order matters, yeah, but it's not the key point here. Why like P does not toward Q? What's the definition of toward, as I mentioned earlier?
C is not
ABD, you can't find it here, right? As I mentioned, that's what I mean by definition. If you want to check whether this tours or not, check the definition of touring. Tour, as I mentioned, if I want to say P towards Q, then you have to be able to find Q in P. Can you find ABD over here? You cannot find this path, right? So that's not true. That's not towards Q. So what we're going to do? We're going to relax the requirement a little bit. Okay, that is in practice. Sometimes it's difficult to satisfy touring. Okay, that is a quite strict requirement, as we will see. Okay. The first relaxation is that tour with side trips. I guess intuitively it allows you to take a side trip and come back. Okay. So the definition is that P tour Q with side trips if and only if every edge in Q also appears in P in the same order. So what is the relaxation compared to the tour, the concept of what is being relaxed?
You have stops in between them.
That's right. So the edges do not have to be separate. you not only find the path, you have to only find the path Q in P, then all the edges in Q have to be consecutive. Otherwise, it's not Q, right? It only requires they appear in the same order, but the edges do not have to be consecutive. So that's where the requirement is relaxed. Then we have the second relaxation called tool with detours. Okay. So P tool Q with detours, if and only if every node in Q also appears in P in the same order. So if you look at this one, compare this one to this one, what is the relaxation? What is being relaxed? The requirement. In the first one, each edge, the two nodes of each edge have to be consecutive, right? Now you don't even have that. Okay, that's where it gets relaxed. So we're going to look at the example. We always use examples, okay, to show the different concepts. Okay. So if I have a path 1, 2, 3, 4, 5, 6. Okay. If I have a test path. Okay. So S0, A, B, C, D. Well, this is A, B, C, B, D. Okay. So if I want to write the path in terms of nodes, so A, B, C, going back to B, D, and SF. Okay. And the Q we're talking about is A, B, D. Okay. Would P is this? Would P to a Q? You cannot find ABD anywhere, right? So P does not to a Q. Does P to a Q with side strip? Yes or no? Yes, why? So basically you have two edges, right? AB, BD, right? So what let me check? If we say P towards Q with side strip, what does it require? The edges have to appear in the same order, right? So we have to find AB, we can find AB here and BD here, but they're not consecutive. If you want to find Q, then they have to be consecutive. But here the requirement is that as long as all the edges in Q appear in P in the same order, then that will be fine. So this is what, yeah.
Did you get Q from the second graph?
We'll talk about
Talk about the top one.
the top one. Yeah, the top one first. We're going to get to the second one. Yeah, the top one. So this is P is on the for the top graph. Okay. So P towards Q with the side strip. Okay. Does P to Q with detours? You can check, right? ABD, right? They are in the same order, right? So as you can see, tool with side strip is stronger than tool with detour. If you tool with a side strip, definitely you tool with a detour. Okay, because if the edges appear in the same order, definitely the nodes will appear in the same order. Okay. Now we're going to get to the second. So I'm going to use P prime for the bottom graph. Okay. So this path is S0, A, B, C, D, SF. Okay. Okay. Would P prime to a Q with a side strip? You do the same, right? You check the two edges. You can find AB, right? Can you find BD? Not. Okay. So P prime does not to a Q with a side strip. Does P prime to a Q with a detour? So you can check ABD, right? Can you find anywhere like ABD appear in the same order in P? So ABD, okay, equals Q with the D2. Okay. So I hope these examples show the differences among the different concepts. So what happens is that in practice, if the test requirement can't be met, can't be exercised without the side trick or detour, you should do that. Otherwise, if it is not possible to do that, okay, then you have to allow side trick or detour. The reason why you do that is that I'm going to give you an extreme example. You know, like there's a statement called do while, right? Okay. So, like for those kind of loop structure, you have to execute the loop at least once. There's no way for you to skip that loop, right? So remember, for that, like if you want to execute N0, N1, N2, that's not possible with the program, right? In that case, you have to allow at least you allow a side trick. Sometimes you have to allow a D2. But the point is that you try your best. Okay, when you try to cover a particular test requirement, you always go tool first. Go for tool first. If you cannot do that, then you relax that. Go for tool with a side trick, and then go for tool with the D2. Okay? So next, we're going to talk about how we're going to actually compute prime path, right? If you want to do prime path test, you have to know how to compute that. Actually, the idea is very simple. And as later you will see, all the algorithms that we discuss in the class will be very mechanical. Okay? You may feel it's like boring, but that's what we want if you want to automate. Okay? So the first step, you're going to find all the simple paths. Okay. Second step, you're going to pick the maximum path. Right? Remember, that's the definition of a prime path. Has to be a simple path, has to be a maximum. Okay. And for the first step, the idea is also very simple, very incremental, right? I'm going to find all the simple paths of length 0. I'm going to extend all those paths to get a simple path of length 1, 2, 3 until I stop. Because you do not allow final internal loop, the number of simple path is guaranteed to be finite. You can definitely stop. Okay? We're going to look at the example to see how we can do this. Okay? So what I'm going to do, I'm going to copy the graph on the whiteboard, and I'm going to do it like step by step on the whiteboard. Okay, to see how we can compute prime path. It's 0, 4, 6, 5. Oh, okay. Yeah, that's important. Otherwise, I'm going to make mistakes. This one. 3. Yeah. A marker, you mean? Okay. You're going to have that on the slide. I'm going to use a marker for my do the actual steps. Okay. So by the way, I do have the slides available on Canvas. I don't know how many of you actually print out them, but okay, very good. That will help you to take notes.
Oh, there's still be 1, 8, 2 to 3.
2 to 3. Okay, very good. Yeah, this is a better one. Okay, so when we go from length 0, okay, what would be the all the simple part of length 0? Basically all the nodes. 6. So I'm going to use the bracket to represent the path. That would be all the path of length 0. Yeah, remember the number, the length is the number of edges you have in a path. Right? I'm going to do length equals to 1. What would be that? All the edges, right? Of length 1. All the simple path of length 1 would be 0, 1, 0, 4. You basically look at the outgoing edges. And then you can go 1, you can do the extension. 1, what the outgoing edges look like? 1, 2, 1, 5, right? Okay. And then we go to 2, would be 2, 3, that's the only one, right? Then we go to 3, would be 1, that's the only one, right? Okay. 4, 4, and 4, 6, right? And 5, 5, 6. And 6, you don't have any time. So what I'm going to do is that I'm going to use an exclamation mark, okay, to indicate this path can no longer be extended. Like over here, because 6 has no outgoing edge, you cannot extend, right? Extend, you have to have an outgoing edge. So I'm going to do this for this one, then this 2 as well, because 6 has no outgoing edge, you cannot add any new nodes after 6. Right? I hope this is pretty straightforward. Basically, you have all the edges here, right? Then we're going to go for length equals 2. So I'm going to do the same. I'm going to look at this path, okay? I'm going to say how many outgoing edges you have, right? So 0, 1, the only outgoing, you have 2 outgoing edges, right? I could be 0, 1, 2, right? And then 0, 1, 5, okay? Now I finish 0, 1, right? I'll finish 0, 1. I'm going to use this to indicate the one I'm working on. So 0, 4, how many, what is the outgoing edge? So it would be 0, 4, 4, 0, 4, 6. Is this a simple path? 0, 4, 4? Is 0, 4, 4 a simple path? Why not? You really have an internal loop, right? This node appears twice, and it's not the first node. So this one is going to be, you're not going to generate that. And I'm going to put, oh, okay, I'm not going to put anything over there. Okay. Because that is, you can extend to 0 or 6. Okay. And I'm going to put exclamation mark over here, because 6 not extended. Then I finish this one, I go to the next one, 1, 2, 1, 2. The only possible extension is 1, 2, 3, right? So I finish this one, 1, 5. I go to this one, 1, 5, 1, 5. The only extension is 6. You the exclamation mark. To finish this one, go to 2, 3. 2, 3, 1. That's the only extension, right? So I'm going to 3, 1, 3, 1, 2. That's one extension. 3, 1, 5, right? 3, 1, 5. Okay. Finish this one. Go to 4, 4. Okay. Can I extend 4, 4? Why not? As long as you add one more node to this one, this loop becomes internal. So you cannot extend any loop. Okay. But this one is still a simple path. So what I'm going to do is that I'm going to use a star to indicate, well, this is a loop, so it cannot be extended. Okay. I finish this one, and this two cannot be extended, so I stop. Okay. Now I'm going to do length 3. So by the way, the way we do this, guarantee that this includes all the simple paths of length 2. There's no way for you to find another simple path of length 2, okay, which does not work here. So we do the same. Okay. 0, 1, 2, 0, 1, 2. The only extension is 3, right? So I finish this one. Go to 0, 1, 5. The only extension is 6, right? There are no other extension. I'm going to put an exclamation mark over there. This one not extended. Go to 1, 2, 3. 1, 2, 3. The only extension is 1, and this is a loop. I'm going to put a stop over there so that I don't have to extend next time. 1, 2, 3. Already done. Okay. Yeah. So we go to this one cannot be extended. We go to 2, 3, 1. 2, 3, 1. One extension is 2. That's a loop. Or 2, 3, 1, 5. Okay. I'm going to finish this one. Finish this one. 3, 1, 2. 3, 1, 2. The only extension is 3. Okay, I'm going to put a stop over here. And I'll finish this one. 3, 1, 5. 3, 1, 5. The only extension you have is 6. I'm going to put it over there. As you can see, as we go along, the possible extensions will become less and less. And you're going to stop. Okay. So we go into length 4. Look at the first one, 0, 1, 2, 3. 0, 1, 2, 3. The only possible extension is what? Is 1, and that's going to make an internal loop. So I'm going to use exclamation mark. It cannot be extended. Okay. It's not a loop, but it cannot be extended. Okay. If you're not going to have another, you cannot extend this to a simple path. This one cannot be extended. I don't have to try that. The only one we have left is this one. 2, 3, 1, 5, 6. That's the only possible extension. So at this point, we have identified all the simple paths. I want to mention that sometimes when you get a problem, like on the exam, especially when the graph may look big, but I'm pretty sure that you're going to stop in a few steps. Okay, so don't get overwhelmed by the size of the graph. Okay, so that's the first step. Second step, we are going to find all the maximum. Okay, so what we're going to do is that we're going to go reverse direction. Okay, because I want to find the maximum one, right? The last one definitely is the maximum one because no one could properly contain this one. So this one is definitely the prime part. Okay, and also I only need to check the path that I have marked. The path that I have not marked, do I have to check that? No, right? Why not? Because it must be extended in the next step. So it must not be the maximum. It must not be the maximum. Okay. So then I'm going to check this one, 3, 1, 5, 6. I'm going to check whether this is contained in any other simple path. You only need to check against the ones that are not in the U, right? Because it has to be a proper containment. So 3, 1, 5, 6, is that contained here? It is. So we're not going to, so this is not maximum. Okay. 3, 1, 2, 3, is that contained here? No, so this. So I guess I'm using the symbol is a little bit overused, right? So I'm going to use plus, okay? So this one is a prime part. This one is a prime part, okay? And this 1, 2, 3, 1, 2 is not contained in any other simple part that you have. You only need to check the ones that are not reduced, okay? 2, 3, 1, 2 is not here, right? So that's going to be a prime part. 1, 2, 3, 1, that's going to be a prime part, right? 0, 1, 5, 6, that's going to be a prime part, okay? 0, 1, 2, 3, going to be a prime part. Because not contained in any other single part. We only need to check the marked ones. 1, 5, 6, is that a prime part? No, right? 0, 4, 6. Yes, right? Okay. And we're going to have to check that. 4, 4. Is 4, 4 a prime part? It's not contained anywhere, right? So 4, 4. A root must be a prime part, because there's no way to be contained in any other part. So all the stars should be a prime part. Okay? That's another shortcut. And that's it. And 6. Is 6 a prime part? No, right? So these are the ones with plus signs would be all the prime parts we have. Okay? Let me check to see if I made any mistake. Anything on the takes a while. Anyway, I guess anyone has the slides, you can check. Did I make any mistake? This should be all the prime parts we have. It's right? Yeah. Let me trust you, okay? Let you check. Yeah. So this would be the prime part we have. On the slides, I have the all the prime part identified as well. Okay. So what we're going to do next is that we're going to generate test part to cover all the prime part, right? That in the end, well, what we really want to get here is a set of test part that achieve prime parts. Now I need to bring it off. It take a while to get it off. But anyway, okay, the way we're going to do it is that we're going to take the longest one. We're going to try to make it a test part. Remember, in the end, we want to get test part. That each test case is correspond to one test part. Okay. So the way we do it is that we're going to do extension. We're going to make sure the test part has to begin with the initial node, right? So look at this one and has to finish at the final node. So this one finishes at the final node. So I only need to make sure we start from an initial node to contain, and we want the this prime part contained in a test part. So what we can do is that from 2, that's the first one, right? I want to find the shortest path, okay, from the initial node to this node. Okay, so in this case, it would be 0, 1. The 0, 1, 2, 3, 1, 5, 6. So this would be a test part. Okay, that contains the prime part. Okay. So after I generate this test part, I have to cross out prime part that might be contained by this test part. Okay. So I'm going to check through. Can you check the next prime part? 3, 1, 2, 3, you will find it here? No, right? So it's going to be there. And 2, 3, 1, 2, 2, 3, 1, 2, no. And 1, 2, 3, 1, 1, 2, 3, 1. Okay, so this one is covered. So I'm going to remove this one. This one is also covered. Definitely, right? Because we created the test part from this one. Then we check 0, 1, 5, 6. No, right? It's not contained in this test part. 0, 1, 2, 3. Covered, right? So we can cross out this one. And the next one is 0, 4, 6. No. And 4, 4. No. Okay, so now we finish this test part. We need to do the same. Then we go to the next one. Next prime part that has not been covered. That's the plus sign. We need to look at the plus sign. Okay. 3, 1, 2, 3. We have to make it complete. We have to make it begin with the initial node, finish at the final node. So this is the node we begin and we finish in the prime part. We're going to do 0, 1, 2, 3. 0, 1, 2, 3, right? Then 1, 2, 3. Then this is the prime part we want to cover, right? Then from 3, we have to make it go to the final node. So it would be 3, 1, 5, 6. Okay. This would be a test path that's going to cover this one. I'm going to cross out this prime path. And I have to cross out other prime paths that might be covered by this test path. Okay. 2, 3, 1, 2 is covered. Okay. 0, 1, 5, 6, no. The next one, 0, 4, 6, no. 4, 4, no. Okay. Then we do the same. We have to create a new test path to cover the next prime path that has not been covered yet, which is 0, 1, 5, 6, right? By itself, it is a test path. I don't have to do anything, okay? And I don't have to check, right? Because no other prime path will be covered by any other simple path. Okay, so I'm going to cross out this one. I'm going to move to the next one. EP4 would be 0, 4, 6. And this is also a test path by itself. I don't have to do anything. So I'm going to cross out this one. I'm going to move to the last one, 4, 4. Okay. 4, 4. Now, I have to begin with 0, right? 0, 4, 4. Go to the final node. 4, 4, 6. Okay. That should be all the test path that we need to achieve prime path coverage. Okay. And I want to point out this test path, they are not unique. You could generate a different set of test paths to achieve prime path coverage. As long as you make sure all the prime paths, okay, are covered at least once by one of the test paths that is detected. But in this class, the approach we use would be the approach I mentioned here. We work on the homework assignments, we work on the homework exam problems. Can anyone check, did I make any mistake on this? You can look at the slides, the test path. Okay, good. That's how we compute prime path and how we generate test path. Network we talk about edge prime path is a very nice topic. Okay. I guess it makes a good trade-off between all path coverage and edge coverage. Sometimes you may feel like edge coverage is not sufficient, not adequate. So it is somewhere in the middle. And we're going to compare that to like data analysis. And people consider like prime path coverage very effective. Okay? And if you look at the way we generate, test the path, it's pretty mechanical compared to like the data flow test later we will discuss. That can be more difficult for you to do. But prime path can be more effective than some of the data flow arguments. So yeah, but the point what I'm trying to make is that the prime path coverage is a very nice idea. Okay, it makes the test requirement, the number of test requirements finite, and make your number of test cases manageable, but at the same time preserves significant fault detection effectiveness. Yeah, but of course it's not all the marks as a good values. Yeah. Any questions about what we did here? The homework problem, basically, you have to do the assignment for the others, how to get